In this short video, I'm going to say a few words about a variation on local optimization that applies directly to assembly code called Peephole Optimization. The basic idea here is that instead of optimizing on intermediate code, we could do our optimizations directly on assembly code. And Peephole optimization is one such technique. The peephole stands for a short sequence of usually contiguous instructions. So the idea is that we have our program, we can think of it as a long sequence of instructions, and our peephole is some window onto this program. So if we have a peephole of size 4, we can think of ourselves as staring through a small hole at the program, and all we can see is a short sequence of 4 instructions, and then we can optimize that sequence. And then we can slide the peephole around to optimize different parts of the program. And what the optimizer will do is it will stare at this short sequence of instructions, and if it knows a better sequence, it will replace that sequence by the other one, and then it will repeat this, as I said, applying other transformations to possibly the same or other parts of the assembly program. So peephole optimizations are generally written as replacement rules. So we'll have the window of instructions on the left, so there'll be some sequence of instructions, and we'll know some other sequence of instructions that we would prefer on the right. So if we see this instruction sequence on the left, then we'll replace it by the one on the right-hand side. So for example, if I have a move from register B to register A, and then a move back from register A to register B, well, that's the second move is useless, can just be deleted, and so we can replace this 2 instruction sequence by a 1 instruction sequence. And this will work provided that there's no possible jump target here. So if there's no possibility that the code would ever jump to this instruction, then that instruction can be removed. Another example, if I add I to the register A, and then I subsequently add J to the register A, I can do a constant folding optimization here and combine those two additions into one addition where I add the sum of I plus J to the register A. So many, but not quite all, of the basic block optimizations that we've discussed in the last video can be cast also as peephole optimizations. So for example, if we are adding 0 to a register and then storing it in another register, well, that can be replaced by a register move. If we're moving a value from the same register to itself, so this is like a self-assignment, well, that instruction can just be deleted, replaced by the empty sequence of instructions. And together, for those two instructions would be, those two optimizations, excuse me, would be able to eliminate adding 0 to a register. So first, this would get translated into a move from A to A, and then the move from A to A would get deleted. And as this little example illustrates, just like with local optimizations, peephole optimizations have to be applied repeatedly to get the maximum effect. I hope this simple discussion has illustrated for you that many optimizations can be applied directly to assembly code, and that there's really nothing magic about optimizing intermediate code. So if you have a program written in any language, source language, intermediate language, assembly language, it makes sense to talk about doing transformations of programs written in that language to improve the behavior of the program. And it's also a good time here to mention that program optimization is really a terrible term. The compilers do not produce optimal code, and it's purely an accident if a compiler were to somehow generate the best possible code for a given program. Really what compilers do is they have a bunch of transformations that they know will improve the behavior of the program, and they'll just improve it as much as they can. So really what program optimization is all about is program improvement. We're trying to make the program better, but there's no guarantee that we will reach the best possible code for a given program.